Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Ever since Tesla entered the casting business in a big way in 2020 with Gigacasting, we've seen rapid innovation in the industry. The 6,000-ton gigapresses Tesla originally used are now dwarfed by 16,000-ton gigapresses, with even larger machines on the way. However, although these machines are impressive and generate a lot of hype, reducing defect rates and producing parts at a higher rate are just as important. That's because those are the key factors for improving part performance and lowering production costs. With that in mind, I've recently come across two innovations by a company called Fondarex that appear to hold a lot of potential for improving quality, increasing production speeds, and producing larger parts out of the same machine size. Those innovations are FX Jet and FX Squeeze. Today, I'll walk you through what those technologies are, how they work, and their benefits. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. First, if you'd like an in-depth explanation of gigacasting, check out my Gigacasting series, which I'll link in the description. In short, gigacasting just means casting very large parts with high-pressure die casting. High-pressure die casting involves injecting molten aluminum into a steel mold, or die, at high pressure. After the metal solidifies, the part is ejected and the casting machine is ready for the next casting cycle. That sounds straightforward, but producing such large parts at high volumes and with low defect rates is a considerable technical challenge. That's where Fondarex comes in. Fondarex has three products that help with those technical challenges by reducing defects caused by gas porosity and shrinkage. Gas porosity is exactly what it sounds like. When the part is cast, gas becomes trapped in the part, which results in a weaker part. The gas porosity can be caused by something as seemingly benign as a drop of water, which can expand by 1,000 times when it goes from liquid to gas. To help solve that problem, Fondarex has a product called FX Vac. FX Vac is a vacuum die casting product, which is a technology I've talked about before. The die is placed under vacuum to remove air and moisture, which in turn reduces porosity. Due to the fact that I've covered vacuum die casting in other videos, and it's widespread in the casting industry, I won't cover it again in depth in this video. The next technical challenge after gas porosity is shrinkage. As the molten metal cools from semi-solid to solid, the crystal structure reorganizes itself. The metal shrinks and pulls away from itself, which creates internal voids and therefore weaknesses in the final cast part. To help deal with shrinkage, Fondarex has two products, FX Jet and FX Squeeze. Let's start with FX Jet, which upgrades the cooling system for casting. A typical cooling system for casting uses coolant loops that run through the casting die. However, the term cooling system is a bit of a misnomer because the purpose is to keep the die at the right temperature. If molten aluminum is injected into the die and cools too quickly, the molten metal can solidify before the part is fully formed. On the other hand, if the molten metal cools too slowly, it can cause the metal to shrink more than it should, which results in shrinkage porosity. FX Jet helps with those issues by providing greater control of the cooling process by using evaporative cooling injector pins throughout the die, up to 192 of them. And the temperature and timing of each of those pins can be strictly controlled so that every part of the casting cools at the ideal rate and at the right moment. Additionally, using evaporative cooling injector pins is a far more effective cooling strategy because vaporizing the water draws heat energy from the die much more quickly than a coolant loop does. As you can see on screen, the result of FX Jet is a significant reduction in porosity, which leads to fewer defective parts and parts that have more consistent strength and ductility. So why weren't evaporative cooling injector pins used in the past? My understanding is that similar technologies have been around for decades, but they were rarely used. That's changing now for two reasons. First, the casting industry is currently undergoing a renaissance due to the need for high volumes of large, lightweight castings for vehicles. That's created a new market and new demands for casting technology. Second, we now have better sensors, computers, and modeling software than we did several decades ago. Those technology advancements help manage the complexity of high-pressure die casting, because the metal has to fill the die in a fraction of a second. In that split second, there's a lot going on because the flow of metal is highly complex and turbulent. Adding up to 192 evaporative cooling injector pins adds another layer of complexity on top of that. Furthermore, with larger parts due to gigacasting, it becomes increasingly difficult to model that turbulent flow as well as manage the casting process, because with larger parts comes greater thickness variability throughout the part, meaning larger temperature gradients. That matters because every part of the casting has to cool at the right rate to avoid shrinkage and part defects. What all this means is that the general technology advancements we've seen in the past few decades allow evaporative injector pin cooling for casting machines to work more effectively and do more new tricks than it could in the past. And that's especially true for gigacastings, which currently there's huge demand for. Interestingly, beyond reducing casting defects, there's a secondary benefit of evaporative cooling: faster production rates from the casting machines. How does that work? In any casting, there are always rate-limiting factors in certain parts of the casting die, such as the metal cooling too quickly and causing bottlenecks in the thin parts of the die, or the metal not cooling quickly enough in the thicker parts of the die. That is, improving the throughput of a casting machine isn't necessarily about more cooling power, but having more precise control of the cooling rate throughout the die. FX Jet offers both: more cooling power and more precise control of cooling throughout the die. FX Jet wouldn't provide a huge production rate increase, maybe low double-digit percentages, but it would still have a significant impact on part cost in an industry where increasing production rates to pinch pennies out of the process is the name of the game. So is Tesla using FX Jet? Given that it's such a new product, my speculation is that Tesla isn't using it in production yet, but I wouldn't be surprised if they've tested it or will use it in the future. That's because typically, the more sophisticated and talented a company is at casting, the greater its ability to incorporate more or newer casting technologies. That, in turn, is because every time a new technology is added to the casting process, although it provides more precise control, it also adds more variables to the casting process. It takes time and experience to understand how each variable affects the casting process and the end product. Tesla has a highly talented casting team, so they have the know-how in-house to tackle the added complexity of a tool like FX Jet and to capitalize on its benefits. Either way, the added complexity means that regardless of whether Tesla specifically uses FX Jet, it'll take time for the technology to become widespread due to the learning curve involved. Next, let's move on to FX Squeeze. Much like FX Jet wasn't necessarily a new idea, but rather brings new functionality and performance to an existing or known technology, FX Squeeze does the same. High-pressure die casting machines sometimes use pins within the die that actuate when the molten metal is injected. Those pins compress or squeeze the molten metal in specific areas at specific times to help reduce porosity due to shrinkage. However, the drawback is that those pins usually run off the hydraulic pressure accumulators that are built into the die casting machine, which are used to squeeze the massive die together. That causes several issues. First, after the casting die is closed and the molten metal is injected, there's often little pressure left over to compress any pins within the die. That is, the available pressure drops as the die is squeezed together, which is just when it's needed to compress the squeeze pins. Second, with a typical squeeze pin system, the pressure supplied by the accumulator is usually about 120 to 180 bar, or about 1 ton of pressure per square inch, and they need more pressure to operate more effectively. Third, the lack of pressure means that typically, high-pressure die casting machines can only support up to 6 squeeze pins, but most use less, at around 2 to 4. Fourth, control of the pins is limited. That is, during the casting cycle, all of the pins squeeze at the same time. Lastly, beyond the pressure issues, conventional pressure pin systems generally have issues with the pins getting stuck due to corrosion. That's because when the molten metal used for casting meets the hardened steel of the casting die and pins, it corrodes them, and higher pressures means more corrosion. So the squeeze pins used to compress the molten metal take extra abuse, which means high failure rates. FX Squeeze addresses all those issues by using a dedicated pressure accumulator, a sophisticated control system, and a better design for their squeeze pins. The pressure accumulator that Fondarex provides with FX Squeeze is capable of 320 bar, or more like 2 tons of pressure per square inch rather than 1 ton. That allows for the control of up to 24 squeeze pins rather than 6, which dramatically increases the force of FX Squeeze over a conventional pin system and the number of locations within the die that force can be applied. Furthermore, each pin can be triggered independently and at exactly the right moment in the casting process with exactly the right amount of force because it has an intelligent hydraulic control unit. That's as opposed to a typical squeeze pin system that activates all the pins simultaneously. So what's the so what here? What are the benefits of all the additional force and control provided by FX Squeeze? As I said earlier, every cast part has thickness variability, and that grows with part size. That in turn means more variability in where and when the molten metal is going to be cooling and shrinking. So, although a typical squeeze pin system might suffice for a casting that weighs a few kilograms, more power and control is needed for a 70-kilogram underbody casting. Furthermore, just like with FX Jet, FX Squeeze will also likely increase production rates by allowing solidification to happen more quickly and without defects. If a casting team uses both, the pressure control of FX Squeeze with the ability to spot cool with FX Jet, it could provide an unprecedented amount of control throughout the casting process, which means lower cost, higher performance parts produced at higher volumes. With that said, given that FX Jet and FX Squeeze are such new products, and casting is such a complex orchestra of pressure and timing, it's not yet clear how much these products can reduce defects and increase production rates. It's the leading edge of casting technology, and it's going to take highly skilled and driven engineers like those at Tesla to push the limits of the technology and see what these machines can actually do. As a side note, tying up a loose end with the squeeze pins, Fondarex claims that they've redesigned the pins on FX Squeeze to resolve the sticking issues from corroded pins. There's no information out there yet on how they achieved that, which I'm guessing is due to intellectual property concerns, but I don't doubt they've made some progress on resolving that issue. That's because Fondarex has a great reputation and a long track record of innovation within the casting industry. As a final note on FX Squeeze, it has a hidden benefit, possibly its greatest benefit. The limiting factor for part size for casting machines is pressure. The greater the pressure of a casting machine, the larger the part it can produce. Some companies would like to produce larger parts to expand their customer base, but purchasing the larger casting machines to do that is prohibitively expensive and risky. FX Squeeze can provide additional pressure so that larger parts can be made on existing casting machines, saving millions or tens of millions of dollars in capital costs. In summary, about 5 years ago, Tesla's need for higher production rates and lower-cost vehicles led them to adopt gigacasting, which has resulted in a jolt of innovation to the otherwise conservative casting industry. In terms of part size, the machines that are now on offer could easily meet any need Tesla would ever have for their vehicles. The name of the game now is reducing costs by reducing casting defects, increasing throughput, maximizing the part size they can get out of existing equipment, and by making better designed, lighter weight parts that have the same strength. For example, as we saw in Sandy Monroe's interview with the executive team at Tesla, thanks to the tight integration between the design team and the die makers, by optimizing the flow of molten metal through the die, Tesla's now able to produce castings in a 6,500-ton machine that would normally take an 8,000-ton machine. That was the result of a hard, multi-year grind from a talented team. FX Jet and FX Squeeze may give Tesla even more room to run to optimize their gigacasting process. But that's certainly not something that's going to happen overnight. That's because every new peripheral that's added to a gigacasting machine adds new variables to the casting process, and therefore a new multi-month or even multi-year learning curve. But for the companies that are willing to make that effort and take that risk, and I'd put Tesla at the top of that potential list, they may be able to significantly reduce production costs. For now, there's no solid information on exactly how much more cost could be squeezed out of existing machines, but as always, I'll keep my eyes peeled and update you if anything comes to light. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers, like my Patreon supporters, generally get access to my videos a week early. On that note, a special thanks to Gar and Rick Jessup for your generous support of the channel, as well as my YouTube members, X subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.